We are very happy to have Faizan Bhat today from IISc. He's going to tell us about bootstrapping string-like models using entanglement minimization and machine learning.
Hello. I'd like to thank Ramesh for helping organize this talk. I'm really glad to be back at ICTS after 5 years. I was a master's student here with Rajesh. And yeah, I've sat in this hall many times and watched a lot of speakers give talks. And even as a student, I used to wonder one day I'll probably be there giving a talk. So yeah, 5 years later, I'm here. So the title of my talk is Bootstrapping String-like Models Using Entanglement Minimization and Machine Learning. As you can see, there's a lot in the title. There's bootstrap, there's string amplitudes, entanglement, and machine learning. So please bear with me while I explain how each of these feature in our work. This is work done with my advisor, Anindya Sinha at IISc, and Annapriya Saha, who is a postdoc there, and my junior, Devapriya. Okay. So I'll begin by describing some puzzles in hadron scattering which people were trying to figure out in the 1960s. And then I'll discuss dual resonance models which were put forward to address some of these puzzles in hadron scattering. Then I'll describe some new results that have come up recently which present field theory representations of these dual resonance or what are now called string models. Then I'll present an S-matrix bootstrap approach to studying string-like and dual resonance models. What we're trying to really answer here is the question, are there other amplitudes which have features similar to string theory amplitudes, but are different in some important ways? So while I describe this bootstrap view, we will have notions of entanglement minimization in scattering processes come in. And then I'll also describe some amplitudes which look very similar to string amplitudes or dual resonance models, but don't actually satisfy what is called the duality hypothesis. Finally, I'll describe some new methods to do the numerics in the S-matrix bootstrap using machine learning. And I'll motivate to why, in what cases machine learning is superior. And I'll finally summarize. Okay, let's begin with some puzzles in hadron scattering. So around the 1960s, proton-proton scattering and heavy ion collision experiments showed that there were higher spin hadronic resonances. And when you plot them on this spin mass graph, you see that they happen to lie on a straight line. And this straight line was called the Regge trajectory. And you had this relation between spin and mass written above, where alpha naught is the intercept and alpha prime is called the Regge slope. Here I'm showing you, these are called Tube-Froschi plots. I'm showing you the one for rho and omega mesons. So in rho and omega mesons, you can see lie at the very bottom. They are the lightest mass states. They have, in this plot, you can see they have mass 1 GeV square and spin 1. But then there's a family of higher spin hadronic states which seem to be connected to these by a linear trajectory. Yeah.
I think the experiments, I don't know, at the time of Tube-Froschi plot, there were no experiments.
Okay. Okay, this is not entirely chronological. Oh. But the Regge trajectories were there. I'm not sure if heavy ion scattering was done, whether they came from heavy ion scattering. But the plots were there. So no, the experimental data was there. No. From proton-proton scattering, it is even produced in electron-electron scattering. You can even study these from electron-electron scattering. So I'm not sure if heavy ion collisions, this plot is from heavy ion collisions, but the experimental data was there, even in the 1960s. Okay, so this is an interesting feature of hadronic scattering amplitudes, but this leads to a puzzle in their high energy behavior. So let's consider 2-to-2 scattering of hadrons, say pion nucleon. The amplitude is symmetric in S and T. Now, if you consider tree level exchange of a spin j particle of some mass mj. Then if you look at the T-channel diagram, you'll have poles in the T-channel corresponding to this exchange. And the residue at the pole is expected to grow as s to the power j, if you have a spin j exchange. It's very simple to see if you have some cubic interaction. Let's say you have phi1, phi2, and some spin j. Then to contract these j indices, you need j derivatives. In momentum space, this will lead to a t to the power j factor. And then if you look at the T-channel guy, you have a coupling here, which will give you p to the power j, and a coupling here, which will give you p to the power j. So the overall thing scales as s to the power j. So this is the intuition. So whenever you have a spin s exchange, the residue at the pole should grow as polynomially as s to the power j. But this leads to some issues with unitarity. Now, unitarity bounds the rate at which amplitudes can grow at large s. Amplitudes cannot grow arbitrarily large at large s. There are famous results like the François-Martin bound. But then even generally, this was appreciated long back that you cannot have arbitrarily high growth at large s. And if this sum were to be truncated to some j max, then this amplitude would start growing at s to the power j max at large s, and this would inevitably violate unitarity. Even if you go to loops and you try to glue two tree-level amplitudes together, the loop amplitudes will start to diverge because there are too many factors of momentum in the numerator. A natural way out is, of course, you don't truncate the sum, you consider an infinite sum, and then it's possible in an infinite sum for the full sum to be less divergent than the individual terms.
If you were to like that at some rate of at least in JP, starting on some interaction, which might be very high, then unitarity would just be guaranteed. Right? If I had to
I think it's the other way around. Because you don't know how to make spin j particles behave well in the high energy limit. That was the reason people couldn't figure out how to write an interacting theory. This is one of the reasons you cannot write down an interacting theory of high spin particles. I mean, in ADS, there are some ways to regulate this growth, but in flat space, people, because of this bad high energy behavior, people didn't know how to construct these amplitudes. But if you take an infinite sum, then we know, for example, the exponential function is a function where each term grows as polynomial in S, but the overall function is less divergent than any of the terms in the sum. Okay. But what happens if you consider an infinite sum? Okay. The thing is, your amplitude, let's go back. Your amplitude on the left-hand side, if it has poles in T, it has to have poles in S because it's ST symmetric. But on the right-hand side, for now, you only see poles in T. So how will this equation work? The only way you can generate poles in S on the left-hand side is if the sum diverges. Whenever there's a pole on the left-hand side, the right-hand side has to diverge for that S. So when you have an infinite sum, this is possible. In a truncated sum, this is not possible. So
if you add all the channels, this was
no.
I thought you said this was only the T channel.
No, this is not only that. These are the T-channel poles, but you can reproduce the entire amplitude from the T-channel poles. So basically, I'll clarify that more. What I'm saying is, if you have an infinite sum, you can reproduce the S-channel poles just from the T-channel, because you can reproduce the poles in the S-channel whenever the sum diverges. If you have a finite sum, it's not possible. Okay, so I'm not saying it always happens, but it can only happen when you have infinitely many terms. Okay, so we're no longer sure if we do need to add the S-channel poles or not, because the poles in the T-channel, the T-channel expansion can diverge whenever there are poles, and then you have reproduced the poles. Okay, but this would be in sharp contrast to what you usually expect in field theory. When you're doing QFT, at every perturbative order, you always have all the channels. You have S channel and D channel. If you have three channel symmetry, you have SG and U all together, plus some extra terms. But all the poles are always there at every perturbative order. So then there's an important question to address here. So which of these is true? Which of these is possible? Are there really amplitudes that you can express just as a sum over S channel poles and just as a sum over T channel poles? In which case you will need an infinite sum? Or is there a representation for these hadronic amplitudes where you have S channel plus T channel and you can actually truncate without violating unitarity? Okay. So in the first case where you actually only have S channel poles and T channel poles is what was called the dual resonance model. The examples of these amplitudes were constructed long back in the 1960s. The first one was put forward by Veneziano, which we will discuss recently in some time. The reason I'm giving this talk is because recently new representations for these amplitudes were discovered, which actually follow this field theory behavior where you actually have S channel pole and T channel pole. These representations were expected, but they were not written down explicitly till this year when Aninda and Arnab actually wrote down these expressions. So before I come to the field theory representation of these of amplitudes of this nature, let's just first discuss dual resonance models. Okay, so dual resonance amplitudes are actually quite old. So this hypothesis that you could actually reproduce all the poles, the full amplitude from S or T channel was put forward by Dolan, Hahn, and Schmidt in 1968. And they had using some experimental data, pion nucleon experimental data, they were able to show that at least for small S and T, there is approximate duality that is respected. Then Veneziano in 1968.
So what is exactly the statement of this duality hypothesis?
The exact statement is that you can express the amplitude in terms of only S channel poles or in terms of only T channel. Whenever you can do that, we say that the amplitude respects duality. So that is this picture. There's an equal to sign, so you can only have this. If you have a sum over all the poles, then we call that the field theory representation, which is what we are familiar with. Okay. Which one?
You say you're allowed to write the way that has only a channel poles or T channel.
Yeah. It will only work if you have infinite sums. Because if you truncate, as I said, you have a bad high energy behavior.
And I can understand this expression of hypothesis. Let's say I take a 5-cube interaction. So I have 1 by S minus M plus 1 by T minus M. Then expand the 1 by S minus M square in some power series. It might look like it doesn't have a pole, but of course it does have a pole because so that is not enough.
No, so basically, if you expand it in a power series, then you know the power series diverges at M square. That is how you know there's a pole.
Yes.
So that is the same thing that is happening here. So you have this expansion. For example, okay. This expansion will diverge whenever there is a pole on the left-hand side. So, okay.
Manifest, but the S channels, then you can also see the divergence from the.
Yeah. So, but on the face of it, okay, to refine it, you can see only one pole manifest, if that is the thing. The S channel poles are not manifest on the right-hand side. What that leads to is this series always has to diverge because you cannot reproduce the poles on the other side if this series doesn't diverge.
Yes, sir. Maybe I must like some question. My question is design statement, because you cannot see the poles. It's not very precise. Like if I wrote this IQ expansion and I expanded it in the power series.
Yeah.
I might say I can't see the pole in S.
No, I think it's not the statement. I mean, it's a function of 2 complex variables, S and T. Yes. You can always look at the poles in one of the variables. Yes. You can always expand in terms of poles of any one of the variables and with some residues, which will be a function of the other variable. That's what he is doing. He is writing this thing in terms of one variable and then saying that that is the same as that expansion in terms of the sum of the poles captures the full behavior of the amplitude, which can also be then written as a sum over the poles of the other variable.
Why isn't that true for some for a 5-cube carry amplitude if I choose to do a Laurent expansion or
It is true. That's what I'm saying. Because you're expanding only around one pole, it is true. But yeah, and then how you would see the external pole from the fact that it diverges.
The ordinary this thing when you just have the one pole term, you don't see anything. I mean, the T-channel pole is just the T-channel amplitude.
Oh, you're just saying you just have 1 by T minus M square. That's it.
1 by M square doesn't tell you the full amplitude.
You need to have 1 by S minus M square times 1 by T minus M square. That is the full.
The residue of the 1 by T minus M square doesn't have any data about it. So maybe that's
it has the power of S. The residue will be a function of the other variable.
In this case, it does. But in my 5-cube trivial example case, it has because the residue is 1.
I didn't understand what is the point.
Sorry, I'm trying to understand what is the precise statement of duality type.
Yeah, that is a particular instance of it. But
What is the general state?
so you can just think of it as a mathematical statement that there is some function of two variables, and you expand in the poles of one variable. It's not guaranteed that you write in terms of the sum over the poles that will reproduce the whole function or in particular in any of the other. It is not true for this trivial for the 5-cube kind of signal. Just knowing the poles and the residues of the poles that you would get the full amplitude.
The duality diagram, this diagram is equal to this diagram, is a statement of duality.
It's a statement of duality, but normally I think the statement, the new thing about the duality, normally in field theory, you add them all, and then it's obviously symmetric. But the statement is that any one of them captures the whole thing.
Okay. We can discuss it a bit later. I don't think what you're asking is hard to address.
Yeah, whatever is possible to exchange in those channels, you sum over all of them.
Okay, good. So Veneziano in 1968, he proposed a version of this amplitude. What he proposed is now called the bosonic string amplitude. What I'm presenting here is the superstring. He presented the bosonic open string amplitude. This is the superstring amplitude. The bosonic amplitude had some issues like tachyonic poles, which when you incorporate supersymmetry go away. So finally you're left with this, but we will use this as a model of a dual resonant amplitude. So this amplitude has an expansion, which you can write down like this. And one thing is this expansion will diverge whenever you have a pole, whenever you hit a pole on the left-hand side. Another thing that we should notice is that the residue at the pole t equal to n by alpha prime is very manifestly a polynomial in S of the order n minus 1. Okay, and we saw previously. So we have S n minus 1, and we saw previously that this corresponds to an exchange of a particle of spin j, or basically. If the residue goes as S to the power n minus 1, that means the highest spin particle that is getting exchanged for that n has to be n minus 1. Okay. So what we see is that this amplitude does exhibit Regge trajectories. That if you are if you're exchanging particles of some mass n by alpha prime, then the highest spin that can be exchanged with that mass is spin j equal to n minus 1. Okay, and so this is the highest spin. This is what we call the leading trajectory, and then there are lower spins as well for the same mass, which are called the subleading trajectories. Okay, so this is one important property of the Veneziano amplitude.
So this Bob's equation discovered recently, or this has been?
No, this has been
obvious that it's equal to that gamma function.
Yeah, this is very easy to prove. You have to use just this. Yeah, it's just some repeated use of this analytic continuation formula. More generally, it can just be proven by looking at poles of the gamma function. And then in the complex plane, if you write a contour integral, you can pick up those poles, and each of those poles will give you these terms.
And whatever the contribution from infinity is, like when you define the contour, you have to worry about.
That is actually very important. So for dual resonance models to have this property, so that is why you don't see the boundary contribution. They actually have a growth such that the arc dies off. That's actually tied into this. That's why I'm about to discuss the high energy behavior. So what you're saying is very important. If the arc at infinity doesn't die off, you will not see this behavior. You will see additional terms coming from the boundary, which will not be pole terms. There will be some additional terms.
Well done. The poles in the S-plane, right?
Yeah.
And the polynomials.
Yeah, exactly symmetric. Yeah. Okay. So the Veneziano amplitude, or this superstring amplitude, was shown to be unitary in d equal to 10. I mean, this was a non-trivial result that goes by the name of no-ghost theorem. So unitarity I'll define more precisely later, but essentially it means that the residues, which are polynomials, they have some positivity properties. Okay, Regge behavior. Regge behavior is the name we give to a small angle large energy scattering, which basically means fixed T and large S, because the angle of scattering, cos of theta, is 1 plus 2T by S, or goes as this. So when you have fixed T and large S, you're basically cos theta is 1, so your theta is 0, it's called small angle scattering. So when you look at this limit, fixed T and large S, the amplitude has a large energy behavior, which is S to the power something plus T. So whenever you have a large energy behavior where in the power you have a T, we call it Regge behavior. So this is not polynomial. It's not S square, S cube. There is T in the numerator, in the power. So this is called Regge behavior. And Veneziano amplitude behaves like this. And this brings me to the point which Raghu raised. If T is positive, or like T is 2 or 3, you can see that if you were to do a contour integral at large S, this will blow up. So you could not have dropped the arcs at large S if T was positive. So you really need T negative to have this representation of this Veneziano amplitude that I showed you. Another property very generic to string amplitudes is called superpolynomial softness. This is in a different limit. In this limit, we fix the angle. The angle is no longer small. And because the angle is given by this, fixing the angle basically means you fix the ratio T by S. So if you fix the ratio T by S and take largest limit, then you have fixed angle large energy scattering. And in that limit, the Veneziano amplitude basically goes as exponential of minus S log S. So this is highly, highly soft growth at large S. And in fact, it was shown that hadronic scattering amplitudes, they do not have a growth this soft. Okay, they're typically seen to be growing as power laws. And this was one of the major drawbacks of this Veneziano model, or the open string model, that this fixed angle large scattering behavior was just too soft. Eventually, this was all in the 1960s. Eventually, with the discovery of QCD, this story, I think we all know, dual resonance models were discarded as models of hadronic scattering, but then they were later reinterpreted as arising from scattering of open strings. Then people tried to incorporate fermions into this, which led to supersymmetry, and then they were generalized to closed string models, and then those theories were interpreted as theories of quantum gravity. So this was the origin of string theory. It was looking at amplitudes of this type, which were meant to be describing hadronic scattering, but sort of failed, but then gave us insights into how you would approach a theory of quantum gravity. So from now on, I may use Veneziano, dual resonance, open string interchangeably. They're all basically amplitudes which have this property that you can write them as completely as just poles in one channel and nothing else. Okay, now let's come to the recent.
It's probably not the main part of your talk, so maybe let's not get hammered. But this first term, this 1 over ST, its residue is not a polynomial in S.
Yeah.
So what is happening with that term?
So the massless poles you can never really write as a polynomial residue. It has to do with the fact that polynomial residues are tied in with locality, and a massless pole basically means long range interactions. So whenever you have long range interactions in the theory, that massless pole you cannot express it as a in a local way. That's why I will come to the partial wave expansion of this amplitude, and the massless poles are always subtracted. So that's why you see the massless pole written separately. What you're asking is tied into the fact that massless poles means long range interactions, and they lead to, you cannot, the local feature that arises from the fact that you have polynomial residues at massive poles is missing when you have massless poles. Okay, now let's come to field theory representations, which are much more recent. Okay, so to get to field theory representations, we have to understand.
You started with the Fauci block. So that's experimental.
Yes.
So these amplitudes do capture some part of the physics actually, perhaps not all of it.
Yeah, so they were seen as amplitudes. The low energy features they were capturing, by high energy they were failing. So that was it was the high energy behavior that basically led to their demise. The low energy behavior was fine. Okay. Field theory representations. All right. Now we'll in the arena of complex analysis, so we can like more rigorously talk about all these questions which Raghu had about arcs not dropping. Okay. So if you have a function which has two-channel symmetry, it's permutation symmetric in S and T, and it has the following large energy behavior at fixed T. Basically, it grows slower than linear. So if the amplitude grows slower than linear, you can basically write it using a dispersion relation. So I will not derive this, but I'll mention the key features. So the amplitude can be expressed in this way, where the first term is the massless pole. The massless pole just stays as it is. And M00 is just the value of the amplitude at S equal to 0, T equal to 0. You can have any constant, but in this case, we fix it to be this. Yeah.
It's 1 plus alpha prime d. It's not minus 1 in the exponent.
Yeah.
I think it should be that there's a typo. No? You have S to the minus 1.
Yeah.
Isn't it plus 1?
No, it's minus 1.
Because the usual growth is this chaos bound is S square. And that
This is
comes
open
down to
string,
S.
right?
So
It's the open string.
This is open string. Closed string will have square.
no, not 2. I'm talking.
Oh, you're saying the.
Not
Could be.
The point is it can grow like S square, but
No, I'm pretty sure it's minus 1. I've checked this. So I mean, it's very easy to check actually. You just have to look at the large n behavior here. And
because here the large, for the this is -1, which is the intercept which you get for the open string, so for the gauge field. So it's not going like S square, which is what the x to S to the 2 plus.
So maybe the 2 that I said was a little bit of a distraction. I'll just check and let you know, it's fine.
But you answer with the residue statement, you would feel in the alpha. You expect from the residue.
Oh.
yeah, no, I'm pretty sure it's -1. I think what you're talking about happens for closed strings. Okay. Yeah. So we'll take this somewhat at face value. The interesting things are, if the amplitude has this behavior, it grows slower than linear. then you only need a few ingredients to reconstruct the full amplitude. What you need is the absorptive part of the amplitude, which is defined as the discontinuity of the amplitude across a singularity. So for example, for these models that we're considering, you just have poles at 0, 1, 2, 3, 4. And the master's pole I've basically separated out. So let's ignore this. So what you're, so the only discontinuities from of the amplitude are arising from these poles in our case. Okay, so you'll get an imaginary part from measuring the discontinuity across the pole. I'll come to make it more precise in some time. So if you know the absorptive part, which is just the discontinuity across the poles, and you know the value of the amplitude at one particular point, can be any point. In this case, I'm taking 0, 0 because it's crossing symmetry. Then I mean, you can get it through contour integration.
Complex function.
Yes. If you give me a complex function, it has this larger S behavior, you can drop the arcs. And then if you know the analytic structure, you can pick up the discontinuities and you're good. Honest to God, contour integral will give you. Yeah, that is an assumption that the branch cuts are all on the real axis. You can modify this to take them into account, of course, but in this case, yeah, they're all on the real axis.
That's all. So if you assume that's the case.
Yeah. Yeah, this will work. There's a little caveat, but I won't get into it. But yeah, what you're saying is true. Okay. So if the amplitude grows slower than linear, then you have this this constant that you need to supply. You need to know the value of the amplitude at one point and the discontinuity. But if the amplitude is yeah, because you can see that everything is manifestly crossing symmetry. Because this kernel is ST symmetric. Yeah, so the discontinuity here, but what enters the dispersion relation is a bit different, you see, is ST by sigma. So this by itself is not crossing symmetric. The combination that enters, that's actually a very good point. That's why these crossing symmetric dispersion relations weren't derived for a long time, because in the usual dispersion relation, which is called a fixed T dispersion relation, you actually just have sigma comma T. And then it's not crossing symmetry. It's exactly this. Yeah. So you compute the absorptive part as a function of S and T, and then just plug in sigma and ST by sigma. Okay. So if the amplitude at large is even softer, this one grows faster, slower than linear. This one is basically.
This is defined for S real life. AS.
Yeah.
And then you don't need to analytically continue that. That function is just defined.
This function?
Yeah.
Yeah, I mean, for example, if you could have a log and then the function is just a constant 2 pi I.
Integration is over the real.
Yeah. Yeah. Okay. So
This ES of T, you don't want it to have any singularities or poles or anything.
yes, that is also an important point. There are certain regions, they don't appear here, but in certain cases, you have something called a double discontinuity, where your discontinuity also has a discontinuity, in which case you have to be more careful. But usually when we apply these relations, we assume we are in a region where the double discontinuity doesn't arise. So just because you asked, let me give you an example. If you were looking at you were looking at an amplitude which comes from a diagram like this, even a triangle, yeah, sure. But this is sort of easier. So if in the S channel you are above the physical threshold, you will have the S channel singularities, but you will say in the T channel, let's say, these are all particles of M square. In the T channel, you want to be below the physical threshold. So then this dispersion relation, then you would want to be in this region, S greater than 4T, less than 4M square, because then you don't have production in the T channel.
Yeah, you can see roughly what you're saying. You should have an additional distinct.
Yeah.
That's the state.
Yeah.
This is very restrictive class of functions, which have like only simple poles or something like that, or have like long simple poles.
Yeah.
That's like this is most field theory amplitudes, except unless you would not follow. I think this one loop amplitude is the.
Yeah. So when people apply these formulas to these kind of amplitudes, they restrict themselves into the region where the T channel production is not there. So T has to be less than 4M square. That is true.
So the validity of this expansion is in some region of the complex.
Yeah.
And then you can analytically. You get this answer.
So no, there is no proof. People don't analytically continue. I mean, of course, if you know the full function, you know all its analytic structure. But in general, this is all you know. For example, for pion scattering amplitudes, the dispersion relations have been written down, and this is all that is known. There is no bigger domain of analyticity than this. So you cannot have production in both channels.
What is the physical reason why restrict the amplitude to sort of follow this?
Yeah, so that is. So let me just explain that. So for example, let's say you have a function in the S-plane, and let's say there is some pole here, and then you have some branch cut here. Okay, and okay, so what can you do? So around this pole, you can do an integral of. Let me just do it in one variable because we only need one variable. Okay. Let me call this some S. Okay. So this guy will just give you f of s because this is done over this contour, and within the contour there is just one pole. Now you can blow up this contour. I can rewrite this contour as something like this. A huge contour. Okay. And now on this contour, if I'm able to drop these arcs, I can write this guy, this f of s, as an integral from, let's say, 1 to infinity. And then I would have to take the discontinuity of the amplitude, s plus epsilon, s minus epsilon. That will give me the discontinuity of f, s prime, and s prime minus s. And if you can't draw up the arcs, then there's a boundary term that you have to add. So that's why yeah.
Last time, like you say, largest, if there's some additional condition, the first time vanished. But if it didn't vanish, if MST grew faster than this, then you would just add some additional terms corresponding to the boundary condition.
Yeah.
So in principle, this is not really a restriction. Why do you need to put the restriction? You can just say that.
So it is a restriction in the sense that, for example, your amplitude satisfies that condition, and then you write it this way. Then, if the first line vanished, then you didn't need any information about the amplitude apart from its discontinuity. In this case, you need additional information. You need the value of the amplitude at another point.
You need one more piece of information.
Then you would need several more constants. Yeah, but then the boundary term would be parameterized by not just one constant. It will be some a plus b times s. Then you would need to know a and b. So
You do this twice subtraction.
yeah. So basically, one factor of s there is giving you one constant, If you had S square there, you will have two constants, S cube 3. If you have nothing, then nothing appears. Yeah. Yeah. Okay.
There's no physical reason for assuming Regge behavior. I mean, what I understand what you said, so that, but, okay, there will be lots of constants.
I think there are some theorems like this classical Regge growth that
Yeah.
Shiraz has been writing
That's
about.
why I had in
So
mind.
this
Yeah.
power of S, that is why I was asking you about the -1 or +1, because this S is kind of marginal. So you can, this Froissart-Martin bound, this basically says that M of S comma T is less than S at large S. So this first line is kind of a natural assumption to make if it was satisfying this Froissart bound. So now in this large N limit or something, this is slightly weaker, and then you have S square, like this.
Yeah,
That is
but-
this Marla-Sena Schenker Stanford bound.
Even there, just to be a little careful, those are STU symmetric amplitudes. If you have STU symmetry, then yeah, then you have that the Froissart-Martin bound. Froissart-Martin bound was not for so for these cases you will have some suppression, some more suppression. So what you're talking about were
Okay, but
pion
power
amplitudes.
cannot be-
Yeah, that is true. The intuition carries out, but the Froissart-Martin bound doesn't directly apply to the open string amplitude. It applies to fully crossing symmetric.
Okay, is that why you have a -1 in the exponent rather than +1?
I think so.
Okay, so if you put the other pieces, then it would be S to the +1. The Regge
Yeah.
would be S to the
So,
1.
yeah, basically. So in those cases, the massless pole, what you're talking about, is basically, yeah, you have some ST plus TU plus US square by STU kind of massless pole, and then this grows as a square. Or on the other hand, in this case, you only have a 1 over S kind of behavior, 1 over ST.
What if you did gauge theory, but you just added all the three channels together? You are doing some color ordered amplitude, right? That's what you're doing. If you just added all three, what would the Regge growth be? Would it be different or is it the same?
No, I think it'll be the same.
Gauge theory also faster.
But I thought in gauge theory, like in any.
So is he talking about? Are you talking about the open string amplitude in all three?
No, not the open string, just gauge. You're talking of pure gauge theory. Like
Yeah, gauge theory amplitude. Like
In pure gauge theory, yeah.
M
it goes like 1 over S.
No, I think it goes like S.
Not okay. It depends for pion scattering amplitudes or gluon scattering. Gluon. No, gluon scattering amplitudes go like 1 over S. I think for because pion scattering amplitudes grow like S. Because that is where this whole thing came from.
Well, he has this S to the J, right? In the numerator, there's S to the J over.
That is the massive particle that is exchanged. That is the spin of the massive particle that is exchanged there. But otherwise, for I think for a gluon scattering amplitude is basically 1 over S plus 1 over. I mean, it's like that dies off very fast.
Yeah, it's 1 upon S.
1 over S. But pion scattering amplitudes or proton scattering amplitudes grow like S. That's why it is in this plots you got this thing. But so if you're scattering particles, then you have all these massive particles exchanged and energy behavior.
There's a model of two blocks, the string.
Correct. Yeah. So those will capture the S to the J behavior. But yeah, that's for proton. It's important. They were trying to capture anyway.
Of interruptions.
Yeah, no, it's okay. As long as I get time to finish this. Okay, so if the amplitude is softer, the first line also vanishes. You don't need to know anything about the amplitude apart from this discontinuity, which is the case I described there, in which case there's no boundary term and you can simply write it in terms of just the poles, which is what dual resonance models are. So for dual resonance models, the dispersion relation is just the second line. And if you have a broader class of amplitudes, which includes dual resonance models and beyond, you have the full once subtracted dispersion. All right. Okay, so this the Regge slope that I was talking about here in the open string amplitude, this is the alpha prime, which is identified with the string length squared. So we will set the string length squared to 1. So we will work in units where alpha prime is always 1. Now, notice that there's a very trivial symmetry of any amplitude, but yeah, let's, for example, take this amplitude. If I shift s to s minus some kappa, t to t minus kappa, then trivially, if I scale s by add do s plus lambda, t plus lambda, kappa plus lambda, nothing changes because s gets s plus lambda, kappa gets kappa plus lambda, the lambdas cancel. So on the left-hand side, okay, let me do it here. On the left-hand side, clearly nothing changes. But on the right-hand side, it is not obvious. So if you do this, this transformation on the right-hand side in the dispersion relation, yeah, just this. Yeah, yeah. And then you, in the shifted variables, you again do a shift s to s plus lambda and kappa to kappa plus lambda. It very clearly doesn't change anything.
First,
There are two shifts.
and then you shift the kappa also.
Yeah, there are two shifts. So it's very obviously, if s minus kappa you shift, in a sense. Yeah. Yeah. So this is, on the left-hand side, this is a trivial symmetry. So yeah. So you shift s to s minus kappa, t to t minus kappa, and then s and t like this. And then you set kappa to 0. Okay. So what you have on the left-hand side, nothing changes. You again get back as the same thing. On the right-hand side, you have a lambda dependence. Okay. And this lambda dependence that you see on the right-hand side, you can do this directly in the dispersion relation. If you do this in the dispersion relation and then apply it to the open string amplitude, you will get this result. Now, this is called the field theory representation of the open string amplitude. And I will describe the lambda dependence in a bit. So the crucial features are you have poles in both the S channel as well as the T channel explicitly. And now the poles are multiplied by polynomials which are not just polynomials in S and T separately, it's a polynomial in ST together. The poles are the same, even the residues at the poles are the same. So if we just look at the pole t equal to n, you will see that this becomes the Pochhammer here. I'm assuming. So if you put t equal to n, you just get this Pochhammer. I'm assuming everyone knows what a Pochhammer is. Basically, this just means that Pochhammer just means this is a polynomial in S, or 1 minus S of the order n minus 1. And this residue is exactly the same residue that we saw in the previous dual resonance relation. So this is a new way of representing dual resonant amplitudes. All the poles are the same place, all the residues are exactly the same, but you have all the poles manifestly on the right-hand side. And you don't just have poles, you have some additional terms, which in field theory we identify as coming from contact terms. Okay. Now this lambda is
I mean the last term is the kind of contact, the 1 over lambda plus n.
Yeah. Yeah. Anything that is not a pole term, we could call it a contact. Okay. So in which case, as Rajesh said, it's the third term. Okay. This is called the field theory representation for reasons that I mentioned. It has poles in all the channels. And there's a lambda sitting there, which is an ambiguity. If you were to perform the complete infinite sum, the left-hand side doesn't depend on lambda. But it's not a property that holds for each term in the sum. Each term in the sum is lambda dependent. So this becomes important. I'll come to why this is important in a bit. Okay. So the truncated amplitude up to some n max will be lambda dependent. It's only when you do the infinite sum that this lambda independence of the left-hand side shows up. Yeah, lambda can be.
And this has some function of three complex variables, ST and lambda.
Yeah.
And do a d by d lambda. I can just get it to Z.
Yeah.
It's easy to see.
We will use it. That is what we use in the bootstrap. Okay, yeah, that's lambda can be complex, but in this case, if you do the large n analysis, you will see that it only converges for real of lambda greater than -1. But yeah, real of lambda greater than -1, you can take complex numbers as well. All right. So these are called field theory representations because they match our intuition of having, what you see in a field theory amplitude. You have some exchanges which come from cubic interactions, and then you have a contact interaction, all three coming together.
You mean lambda times itself is contact?
Lambda times this. Yeah. So there is no pole. It's basically a polynomial in SNT.
But here there's no truncation. J max, you put J in the next slide when you wrote down. Yeah, because here it's a sum over all the
Yeah. So I'll come to why there's a J max. So in field theory, you don't have infinitely many fields. You don't have infinitely many cubic couplings. You always have finitely many cubic couplings. So a true field theory representation, if you want to call it, it should really respect the properties that we know and love in field theory. It should really show them even when you truncate to some J max. To reproduce everything exactly, you need to take J max infinity. But even if you truncate to some, let's say J max, some 10, 20, 100, some finite J max, it should still, one, not violate unitarity, respect Regge behavior, and not diverge apart from the places where on the left-hand side you have poles. So it can only diverge, that I didn't come to.
When you say it allows truncations without violating unitarity, this is tree level.
Yeah, everything is tree level. Yeah.
So just positivity.
Yes, just positivity. Okay.
Yeah. What's about?
Yeah.
Yeah, I would think it was that you go like S to the J. And that kind of
Yeah.
goes too fast. If the amplitude goes too fast,
So I think at tree level, the statement is that, there is some bound. Yeah.
Yeah, it's unbounded with very cross-section.
That is true.
Yeah, can you show why that happens?
I actually, let me see.
Yeah, that is in one loop. So I think all it means is positivity, probably, because that boundedness argument comes if you take the imaginary part.
Yeah, but that's the argument he himself gave in the first slide.
Correct, I agree. Okay, I don't know whether you should call it unitarity, just positivity.
Yeah. Oh, let me say what it means. It basically means that you should see this Regge growth even at small s. It should smoothly interpolate.
The argument slide was these amplitudes go like S to the J.
Yeah.
That's like it's fast. S to the J max.
Yeah.
It's fast. But you want probabilities to be one.
Yeah.
It seems if you cut it off at finite end, you will get the S to the J because that programmer will give you the S.
Yes.
How are you getting around the argument?
So I don't think this doesn't cure that. What this cures is the fact that you don't have your sum won't diverge at the poles, because all the poles on the right hand side have been taken into account. There is no pole here, So this representation only diverges at the pole and nowhere else. It will converge around S equal to N as well.
I am confused. I could have written down some effective field area. And some S to the J and so what's so special? And what's special about this is when you take the sum to infinity and let's say I just wrote some effective field area. I wrote S to the J, E to the J.
Sorry, I don't understand.
Sorry, let's say I change that bracket to something else.
Okay, so here, yeah,
And I say that's my effective field area.
yeah, yeah. No, I agree with you. If you truncate, it will violate unitarity. Yeah. So that is a feature of these amplitudes. That's why you really need to take the infinite sum.
That next slide, you should probably just say positivity rather than.
Yeah, I will. Tree level unitarity is just positivity.
The residue is.
I will. Yeah.
At any pole, because that's your, you have a positive answer. So that's the only three-level sort of constraints.
But I could have made up any amplitude that have these properties, right? I could rotate to the 2n, T to the ST or whatever.
No, see what happens is why this combination. Your question is why is this combination special? Right? Yeah. So, for example, one feature that this amplitude has is if, as I said, if you go to T, near T to the power near the pole in T, this is exactly the residue is exactly what you would see in the fixed T dispersion in the dual resonance model, basically in the previous expression. So if you go near the T equal to N pole, the residue becomes exactly what it was before, and then you have basically reproduced the entire amplitude. Now, but what about this term and this term? These two terms need to cancel each other. So whenever you're approaching this pole, this and this has to cancel. Whenever you're approaching this pole, this and this has to cancel. And if you're in the intermediate region, where you're neither near this pole and this pole, you're basically double count. And then the contact term has to cancel all of that. So it's a very tightly knit structure where all of that is ensured.
Maybe you should go on it.
What I'm saying is that behavior is respected approximately when you truncate. So you can approximately, if you kept it to 100, you would approximately see that these things are canceling each other. I mean, I agree that probably is not.
But just a note on time, you're only 12 out of 35 slides. So
Yeah, okay.
So we should go on for another half an hour, maybe stop at around 5. It's 4:30
Sure.
right now. 20, 25 minutes. Is that okay?
Sure.
Started a bit late.
A bit late, okay, half an hour.
Okay, let me just then go as fast as I can. Yeah. So if you do the partial wave expansion, this is what Adesh was speaking about. So if you take the absorptive part, it's just poles, and the discontinuity across the poles is the delta function. And then you do a partial wave expansion, which is basically expanding in Gegenbauers. Then the statement of unitarity, which I write here, is just that these partial wave coefficients have to be positive. Okay. And in addition, we had these constraints that I mentioned, that the derivative with respect to lambda of this RHS, this representation has to go to 0. We call them field redefinition independence. We can get into why they're called field redefinition independence later. And K is just derivatives. You can take any number of derivatives, and they should all be 0. So these are two constraints. The reason I mention them is when we do bootstrap, I will be using both of these constraints that this dispersive representation has. Again, dual resonance models only need the second line. Beyond dual resonance, you need to keep the whole thing.
First line, second.
The second line is just the unsubtracted guy, and the
No, the first line is, that's just.
It's the same equation. It's one full equation.
Right. But the second term in the first line,
Yeah.
last term in the first line, that's just some constant piece.
Yeah, these are just some constant pieces. Yeah.
So, okay. No, I thought you said something like you were making some distinction between the.
No, I'm just saying. Yeah, it's just some constant. So this constant in the first line will not be there if you have a dual resonant amplitude, which is, as we saw, grows softer in the largest limit. If it grows slower than linear, then you have the full dispersion. You have the full partial wave expansion. Okay, now let's come to the S-matrix bootstrap part of the thing. The bootstrap approach, we all know, is probably we all don't know, is an approach where you don't try to like have a Lagrangian and then solve the equations of motion and compute scattering amplitudes from there. You physically just say what are the physical properties I expect from an amplitude. Generally, they are unitarity, crossing symmetry, Lorentz invariance, some analytic structure, which follows from typically causality. And then we say, if I just impose these on the space of amplitudes, how much can I gain? How much can I bound this space of amplitudes? And this is basically the only general approach we have to compute in a vast variety of scenarios, non-perturbative scattering amplitudes. For example, PINN amplitudes have been constructed using the bootstrap by various people, including our group at IISc. Okay, now we want to bound the space of non-perturbative scattering amplitudes. To bound something, you need to parameterize the space first. So we parameterize these amplitudes by their low energy expansion. Low energy expansion is basically written in terms of Taylor expansion in S plus T and ST. So these coefficients of the Taylor expansion are what are called Wilson coefficients. W00 is basically just the amplitude at 0, 0. An expansion of this kind, for example, if this is the S-plane, you only expect such an expansion to hold below the discontinuity. As soon as you hit the discontinuity, you get divergence. So this is the low energy expansion of the amplitude, and the coefficients in the low energy expansion are called Wilson coefficients. After I have subtracted out the massless. Yeah, there should be a massless pole here as well, which I have subtracted off. Okay, so what are the bootstrap constraints that I will impose? So we will work in D equal to 10, because that is where we know the superstring amplitude is unitary. And we will impose crossing symmetry. Analyticity will basically be only simple poles at S equal to n, whatever the open string amplitude has. Residues at poles, we will basically take exactly the open string spectrum and nothing else. And unitarity, as I showed you, is CLN positive, and these are lambda independence. So these are the constraints I will impose numerically. One, mathematically, the prescription I showed you always works.
But so that is the answer that you showed, which happens lambda.
Yeah. No, the amplitude is always lambda independent. The representation always has a lambda. The representation, the right-hand side, this guy is lambda independent. There's nothing called lambda here. But this representation has a lambda, and it's only these. It's basically this lambda independence is basically constrained on the partial wave coefficients. Not any set of partial wave coefficients you plug in here will ensure that the sum is lambda independent. I see. Okay. Sorry, I had to go through this a bit fast. Yeah, but lambda independence is a constraint on these CLNs because it only arises for a particular set of CLNs, that's why we impose this as a bootstrap constraint. There is physics. We can talk about it later. Or let me just, okay. So let's say we have some light fields phi 1, phi 2 in the theory and some heavy field, some psi. Okay. And sorry, can you see? And then let's say you have some cubic interaction of the kind phi 1, phi 2 psi. Then let's say this is a heavy field. So you could imagine doing a field redefinition like this. Okay, and so lambda is the field redefinition parameter. And then let's say in this theory, I integrate out the high energy modes. So that is basically effectively truncation to some n max. So in that truncated theory, I still have this additional lambda dependent term. This additional contact interaction appeared. So, and the statement is in the full theory, when I had not truncated, this field redefinition should not have mattered in the amplitude. But if I truncate, this field redefinition is basically a signature of the high energy modes. So we can discuss this more later, but this is the brief physical description. Okay, so so what are the questions we want to address via the S-matrix bootstrap? So one question is, in the space of bootstrap consistent scattering amplitudes. By bootstrap consistent, I just mean amplitudes that satisfy these conditions. That satisfy duality. For example, like the open string. In that space of amplitudes, is the open string amplitude special in any way? And the answer is yes. The open string amplitude appears to minimize the amount of entanglement generated in the scattering process. I will explain that soon. So the second question we want to answer is, are there consistent amplitudes that have all these properties, the same spectrum, unitarity, etc., lambda independence, but which go away from duality? Basically, I had given you this dispersion, this representation, and I said, if the amplitude satisfies the full, needs the full dispersion relation, then for dual resonance, you only need this part. But if I demand that the amplitude satisfies the full thing, then if I impose these constraints, is there a solution? Is there a solution to this that satisfies this dispersion relation and positivity and field redefinition? We know for this case, if I don't have the first term, for this case, there are solutions, there are open string amplitudes. But are there amplitudes beyond this where you can impose beyond the duality hypothesis? Okay, and these are important questions because duality hypothesis was never really there was no strong experimental support for it. So Greenshaw's written in the chapter 1 of their book actually say the duality hypothesis was never had more than slender experimental support. And the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis.
So that is described in S-matrix for string case, or that is described?
Yeah.
Some S-matrix, some consistent.
So this is tree level open string, so no, but we also do closed string. I will not describe that, but tree level closed string we also do. So there also we find a space of amplitudes which satisfy all the bootstrap constraints, or like constraints like Regge behavior, unitarity, same spectrum as string theory, but then don't have duality. So these are just a different class of amplitudes. Okay.
There should be such scale. What we find.
I mean, so that is the whole approach of bootstrap. So when you say, do you expect something physically, we make it precise. What do you mean by expecting physically? You mean theories that satisfy crossing symmetry, analyticity, So this is like a rigorous way of asking the same question.
I can deduce something for the CFT, but we expect that the CFT really exists, some cases at least.
Yeah.
But here, I mean, are you saying that you expect that this PTA is quantum PTA is exists in this problem?
Expect, we construct them. I will construct these amplitudes. I will show you what these amplitudes look like. Exactly. No. It's, construct mean at the level of the amplitude. In general, it is true that all these amplitudes that I show you, which look interesting, if you were to do 2 to n scattering and then impose unitarity, they would all be ruled. Sure. This is just at the level of 2 to 2 scattering amplitude, you have some consistency conditions which are imposed.
of this will lead to the discovery of field area, which are completely consistent that are not earlier. Like, is that
Yeah.
that's
Not field theory and maybe string theory, something. I mean,
Some-
maybe some other thing we haven't.
so some of the bootstrap will give us some new thing which we have.
Yeah. So
Perhaps, I mean, as he said, it's only a necessary condition, not a sufficient one. You like to impose many more constraints to see that is consistent, but at least it begins to carve out the space.
all right. So even Dolan Horn-Schmidt, they said that there should be representation that is basically Regge plus resonance minus some additional term. Regge is basically T-channel pools, resonance is S-channel pools. So even they said the true representation should actually have some additional term which avoids the double counting here, which is the form we saw in the dispersion relation I mentioned.
Duality then that considerably weakens the constraints, or it's not. I thought duality is a very strong constraint.
I mean, in the sense of dispersion relation, you can just see it as the largest constraint, right?
Largest.
It's basically a restriction on the largest behavior because whenever you have soft behavior, you have fixed T and then you have. So in that sense, I don't know how strong going from, one more power of S. I think it's a very strong constraint. Yeah.
Yeah, but I mean, presumably you will go on to answer at least
part of
these questions.
Yeah.
So I just want to know for you, in a sense, that when you say there are consistent amplitudes that deviate from duality, presumably they are much less constrained. There's a much larger space of amplitudes.
There's a much larger space of amplitudes which are within which lie the string amplitudes. Yeah. Okay. Okay, now let's try to answer the question, what do we mean by entanglement generated in the scattering process? So there was some recent work done by these authors. So they basically tried to compute, unfortunately, now I won't have time to go into detail. They were trying to compute how much entanglement is generated in a scattering process. So in the beginning, let's say you have some 2-to-2 scattering, you have some asymptotic particles well separated. We assume they're unentangled initially. And far away from each other. Then they go through scattering and then you measure them in the far future, far away from each other. The question is, are they entangled in the asymptotic future? Did the scattering generate any entanglement? And they were able to answer this question via the language of the scattering amplitudes. So they basically said that I will just come to the result, that the amount of the change in entanglement, which is delta, what is this? Delta E, is basically given by the scattering amplitude, the elastic forward part of the scattering amplitude. So K1, K2 going to K1, K2 configuration. And so in this case, we are looking at, because we are speaking of entanglement, these are gluon scattering amplitudes, and what we are measuring entanglement is in the gluon helicities. So alpha beta represent, so alpha beta basically means particle alpha, particle beta go to particle alpha, particle beta. So there's no new production, and the momenta are also the same. So this is called the elastic forward scattering. Okay. So basically, the change in entanglement in a scattering process is related to the imaginary part of the amplitude in the T.
So, can you say in a sentence or two why the entanglement would be related to this? I know this is not your result, but this is to leading order. Yes.
This is tree level, yeah.
So the entanglement is
I honestly don't. This is the result we picked up. I don't have any intuition really for this.
Reasonable to expect something like this weak entanglement because you're interacting really.
Yeah.
You're asking
why is this forward scattering amplitude?
Yeah.
Yeah. Scattering will capture the entanglement.
Yes,
you look at the final state and you look at the.
Very similar, but the formula actually. I don't know.
Yeah, the imaginary part, that is like the optical theorem. If you have, then it's the mod square, I guess.
Yeah. It's the total cross section. I really don't have any intuition.
And this is the usual entanglement entropy, right? The E is defined in the usual way.
Yeah, you have two particles, you trace over the degrees of freedom of the other particle, and you're just left with the density matrix for the first
But
particle.
it doesn't seem to be traced so long. It seems to be this one minus
Yeah.
trace.
So this
It's
is
like the second derivative.
so this is called something. This is called linearized entropy.
It's not the one Neumann
Yeah.
purity.
So the statement is that this entropy is von Neumann entropy linearized around the maximally mixed state. So that is what the linearization is. Yeah. So I'll just quickly mention this, that, okay, so now we want to compute this, this change in entanglement for the gluon scattering amplitude. So for this purpose, now you need to bring in the tensor structures. And so this is the tensor structure for the gluon scattering amplitude. And Fi mu nus are the field strengths for the ith gluon. So now we need to take the forward limit because that's what the formula said. In the forward limit, this tensor structure simplifies to this. And you basically have an S square. So what we see is that the amount of scattering generated is given by, so we had the absorptive part. Okay. So it comes with an S square and that is the residue. So to make the whole thing finite, we basically measure moments of this entanglement divided by S square, because otherwise this blows up if you do this integral. And it turns out this we call this the first finite moment of entangling power. Because there's an S square, we have to divide by an S square. I could have also considered S cube, S4 suppressions. Those are second and third finite moments. So we will only look at the first finite moment. And it turns out that the first finite moment is basically just the negative of the Wilson coefficient, the first Wilson coefficient W00. Basically just the amplitude at S equal to 0, T equal to 0. All right, so now what is the bootstrap? Okay, now this is like mathematics only. This is the bootstrap problem that we want to solve. You have an expression for the Wilson coefficients in terms of CLNs via the partial wave expansion, and also for the first moment of the entangling power. So the problem is find the set of CLNs that minimize the entanglement, the first entanglement power, or maximize W00, same thing, under these constraints. CLNs are positive for this range of L and N. This comes from the open string amplitude and unitarity. We also do impose two more constraints. We fix the first two Wilson coefficients to the open string value. So if you take the open string amplitude and compute its Wilson coefficients, you will get these values. So we fix some low energy data, basically fixing some data in this region. So this is the first massive pole. So we are fixing these coefficients determine the value of the amplitude in some small s, small t region. So we have fixed some low energy data and we have fixed it to the string theory values. And then we are imposing these unitarity constraints and these lambda independence constraints on the amplitude. By amplitude, I just mean CLNs because these are the partial wave coefficients. Now, this is an example of a linear optimization problem. And Simmons-Duffins had made this package called SDPB, semi-definite programming for Bootstrap. So SDPB can handle semi-definite optimization problems. So this is a linear optimization problem. It's a subclass of semi-definite optimization. So we use SDPB to solve these problems. And I will discuss both amplitudes which satisfy duality and which don't. So as I said, in the two cases we use, for the duality satisfying amplitudes, we throw away the first term. And yeah, so these constraints, these lambda independence constraints, we impose in some, because it's a function of SNT, you need to impose it in some domain of SNT. So we pick some random domain of SNT generated by random numbers. Notice that in this domain, we don't really go to large positive S and large positive T. That is because in that region, at least the open string amplitude becomes huge. And there are some issues that arise from it becoming huge, which is why we need the machine learning part. So it'll come later, but just one statement that we don't impose these constraints in the largest large T. space, only around the smallest small t and yeah, this quadrant. Okay, so so these are the results. So when we impose this entanglement minimization and we compute these partial wave coefficients for the amplitude, the bootstrap gives us these values. So these are values for the sub-leading trajectory, sorry, for the leading trajectory. Leading trajectory is basically was CLN, L was n minus 1. So this is the leading trajectory. And you can see that the amplitude that the bootstrap gives you from entanglement minimization is extremely close to the actual superstring amplitude. So this is the leading trajectory, this is the sub-leading trajectory. Okay, and if you actually plot the amplitudes, they basically lie on top of each other.
This additional term that you have,
No. So these are results with duality. So this is on the class of amplitudes which satisfy duality. For those class of amplitudes, that additional term is not there. Those subtraction constants that I showed you.
that's almost a missing.
Yeah. These constraints, and you fix some low energy data, you have to fix the first two Wilson coefficients to the string value. You will get something else. You won't. Yeah, you won't get the string amplitude.
Are you saying so there's actually a two-parameter family of amplitudes?
Two-parameter family of amplitudes that satisfy the bootstrap constraint. I will show you the family as well. I will show you those amplitudes as well. Yeah. I mean, I will show you they exist. I won't show you their exact form. So, but in this case, I fixed some low energy data. I basically fixed something in this region. Two parameters that determine the behavior of the amplitude in this region.
S plus T and
yeah, ST. Yeah.
This might not be so surprising, right? Higher order terms are somehow by the constraints and entanglement constraint, are somehow being determined by lower order. It might not be so surprising that if you fix a few terms in the beginning, you start getting higher order terms.
So
it's not obvious, but right now I'm just saying that the uniqueness seems to be actually looking at some very four-dimensional zero region of
not really. So, for example, here I plot the amplitude, and it is predicting all the resonances up to S20. While as what I fixed was basically below the S equal to 1 region. So why is it producing the entire amplitude up to S20 is non-trivial. Because you only fix some low energy data, you only expect it to agree in some low energy region. But we see that entanglement minimization as well as these lambda independence constraints. So it turns out if you want agreement up to 20, you need to impose this lambda independence constraints up to in a region ST up to 20. So these lambda independence constraints are actually what lead to this agreement to high values of S. Yeah. So basically the statement is you fix some low energy data and you impose these constraints and you minimize the entanglement. And it seems to pick out the string amplitude up to a very large value of S, which is it relates the full amplitude at one point to the full amplitude at another point. So yeah, I would say.
You should just take some mysterious I'm trying to understand how should we understand this? Because it's a very surprising result.
It is surprising to me because no one told you that you minimize entanglement and you pick up superstring amplitude. If you maximize entanglement, you would find something completely different.
Yeah, I just want to think you and fix some low energy data.
Yeah.
With some very special values. Then you pick up the rest of
To the open string values, and then you pick up the rest. So somehow only fixing the low energy data helps you pick the open string amplitude to a large values of energy if you minimize entanglement. Okay.
Can you conclude in like 5-6 minutes?
Okay, I'll just show you the plots. Okay. Yeah, so these are all the amplitudes we find in the, so now my W10 and W01 is not fixed. We we tune W10 and W01, and and for each value of W10 and W01, we minimize entanglement. And then we plot these scattering amplitudes. And this is a heat map of how well they satisfy dual resonance. And the string amplitude is in the blue region, satisfies dual resonance up to, there's a truncation. Up to n max equal to 30, it satisfies dual resonance really well. But this is basically a matter of conversions. Up to n max equal to 30 string amplitudes, and then there's a family of amplitudes which are called hypergeometric deformations of the string amplitude, which also satisfy dual resonance very well. So so this is just telling you what Suraj asked, that yeah, there are other amplitudes which arise if you pick different values of W10 and W01, and yeah, only if you pick the low energy data to be string value will you pick up the full string amplitude. Okay, now coming to what Rajesh was asking. Yeah, this is what you get when you impose, go beyond duality. So this is basically the same thing. Now I'm using the full dispersion relation. And in the full dispersion relation, there was an unfixed parameter W00. We basically fixed that by demanding that duality be satisfied at t equal to 0. Basically, at low energies, duality should be satisfied, and at large energies, it should not be. And this region is much bigger. For example, W01 is now allowed to go negative. And in the previous plot, W01 could not go negative. So,
but how do you relax duality? What do you mean by relax in your scheme?
so for example, I don't have the plot because I wasn't expecting this much curiosity. But for example, this black star amplitude, if you pick this amplitude from the bootstrap, at large energies, it will go to a constant. And then if you try to write it for example, using the fixed dispersion relations, you have to introduce that constant, because it goes to a constant at largest. You cannot drop the arc. So this is an example of an amplitude which cannot be written just in terms of poles. It will need some additional constants apart from that. Okay. So there is some interesting feature that these guys satisfy, which is called Polchinski-Strassler type transitions. I won't go into it. Okay, let me just skip this completely. Okay. Now bootstrap using machine learning, in particular what I use are physics-informed neural networks. Now let me just quickly mention, it's because this is just tool, it's technical. So when we impose these constraints, these lambda independent constraints, we impose them in the form derivatives of the amplitude should be within some tolerance. And we set some small tolerance. Epsilon in my case was 10 to the power minus 9. But nobody told me that if I truncate the amplitude to some n max 30, because this lambda independence is only supposed to arise when you do the full sum. Nobody told me if you truncate it to some n max 30, your amplitude should satisfy lambda independence up to this small tolerance. Okay, so it is sort of unreasonable to put this tolerance this way. Yeah, that is what I mentioned here. An example is, for example, for the open string, because it's a gamma function. So for large t, it can basically be of the order 10 to the power 6 MST. And then what does it mean for the derivative to be small? The derivative could be 2. Okay, this is very small if you see the variation with respect to lambda for n max 30, let's say. But what I'm imposing is the derivative should be 10 to the power minus 9. So what you really should be imposing is not just the derivative should be small. It is constraints of the type that the derivative divided by the amplitude, this ratio should be small. So that even when the amplitude itself is large, and therefore its derivative will also be large, what actually should be small is the ratio. So we would like to impose constraints, or it's much more reasonable to impose constraints of the type, of this type, that m at lambda 1 minus m of m at lambda 1 by lambda 2 is very small, or the derivative divided by the amplitude is very small. But the trouble is, these guys are nonlinear in the CLNs. These guys are nonlinear in the parameters, okay, because there's an amplitude in the denominator as well. And SDPB, in fact, most bootstrap studies never impose nonlinear constraints of this form, because essentially the only tool most bootstrap studies use to impose these constraints is SDPB. And SDPB can only handle linear problems and non-linear and semi-definite problems. So linear problems are of the type some matrix A acting on some xm, and you want this to be less than some cn and some bn. Okay, so this is a linear operator. So these are linear constraints, and your job is with respect to these constraints, you need to find the solution x of m. Sorry?
Let's say you don't normalize it, and you just do the semi-definite programming using the unnormalized.
That's what we did.
Then you don't need to do that.
No, but the thing is, that's why I showed you this plot. So in a sense, we somewhat cheated. I didn't go to the largest large T region. That's only because I know the open string amplitude in that region is large. So I cannot impose this constraint. It's sort of cheating because if you're doing bootstrap, you're not supposed to know what you're bootstrapping. So I am sort of back calculating the tolerance for my app. So if I didn't know the open string amplitude, I had no way of knowing, okay, if I didn't know the open string amplitude and I basically, let's say I uniformly distributed my constraint. In this region, the open string amplitude derivative is order 1. Then I could potentially rule out the open string amplitude as well, which of course we don't want to do. I will come to an example of that form. Okay, so what these neural networks allow you to do is impose nonlinear constraints. So if you want to learn a 2-variable function, for example, I want to learn CL of n. So I have 2 variables, L and n. So your neural network has 2 input layers, and then it has some hidden layers which do the learning, and then it spits out some CLN. So a neural network is basically just a huge map with several tunable parameters. So so let's see what is each neuron doing. Each neuron basically takes, for example, this neuron will take an L value and an N value. Then it has some weights. It will multiply each L value with some weight and each N value with some weight. And then it will add something called a bias. So it basically forms a linear combination. So okay, so this is the previous layer outputs. In this case, the previous layer is L and N. So YKs are basically K is 1 and 2. So it will multiply each value of L with some weight factor and each value of N with some weight factor. And then it will add some constant, which is called the bias to it. And the whole thing is then acted upon by some nonlinear function. These are called activation functions. And there have been results that a function of this form with tunable parameters, they're called universal function approximators. Basically, if you were allowed to take millions and millions of these parameters, you could basically approximate any function. In this case, we want to use this to approximate CLNs. Okay, and you have to pick some nonlinear functions, sigma and gamma. So sigmas, I pick this function, max of 0 and x. It's called a ReLU, rectified linear unit activation function. And in the final layer, I pick gamma. Gamma is basically called the soft plus activation function. This ensures that my CLNs always come out positive because whatever comes from here will go into this x, and then gamma of x is always positive. So my neural network is basically designed to only input unitary solutions because of this activation function at the end. Okay, and I have 2 neurons here in the first layer. I have 2 hidden layers with 64 neurons, and then 1 final layer with 1 neuron. If you count the number of parameters I'm using, these weights and biases, which I call theta I, my neural network has 4,417 parameters. Okay, so how does a neural network learn? I won't go into details. You basically define something called a loss function. So loss function is whatever, in this case, what we define is the following. Whatever quantity you want to minimize goes here, plus beta 1 times some constraints, beta 2 times constraints. So this is this here I'm fixing W10 to string value, W01 to the string value. And then here L tilde, I will impose. L tilde is basically these constraints that I said I want to impose. So for example, this. And the neural network basically, it learns iteratively. Every iteration, it will start with some random values of these parameters, theta I. Some random values it will initiate with, and then it will compute the CLN. And of course, it will get some CLN which is very different from the actual solution. And with that, with those parameters, when it will compute the loss function initially, it will be huge. Let's say it's some 10,000. Then every iteration, it tunes the parameters in the direction in this parameter space of thetas, which minimizes the loss, which you have defined.
Why do we gradient descent and CLNs? Why do you want to write the CLN as some complicated function of LN and then do gradient descent in that function? You already have a loss in terms of CLN.
Yeah.
You could use gradient descent.
You could, yeah.
That's much simpler. Right? Why like, what's the point of this? I'm not understanding.
This is just a framework that allows you to do it.
Gradient descent is gradient descent. You just do it your user way. Why did you introduce all these intermediate ways?
Yeah, I agree. We could have just done it in the original variables.
It's very confusing, right? You're doing gradient descent, but writing CLNs as a function of N and N.
Yeah, we're imposing CLNs are functions of other parameters.
Some efficiency way that
So the thing is, when I started doing this, my example application was not this problem. It was here we only have to impose positivity, but positivity on CLNs. Typically, you don't have CLNs. You have CL as a function of S, because you only have N's here because you have residues at poles. If you have a branch cut, then you won't pick up individual residues at ends. You will pick up, the partial wave coefficients are entire functions of S. And in that case, you really need to have a way to parameterize these functions in some way. You need a basis for these functions. In this case, you really don't. So this was not my target problem, but this is basically a proof of principle that you can use physics-informed neural networks to do nonlinear constraint optimization. So what you are saying cannot be done if, for example, I had branch cuts and my, we can discuss. Okay, I'm almost done. Yeah, so for example, so these constraints, so the neural network tries to minimize the loss function, and therefore, so you have to pick these beta ones large. Only when, let's say, if beta 1 is 10 to the power 4, it will make sure that you have satisfied this too, at least 10 to the power minus 4, this term. So this is the loss function. This is basically the only thing you need to, this is the only input.
That's a judicious choice, this loss. Is there some,
in fact, I had a related question. From all that, I know nothing about neural networks, but from whatever talks I've heard, I always hear people talk that in this gradient descent, you impose the constraints not with a square, but with just the modulus.
Mod. I mean, you can do both.
That is more efficient, or somehow that is supposed to be faster.
I honestly, I've tried both. I didn't get a huge change in behavior. And really, with these things, people are still studying all of this. No one really knows. No, nothing sacrosanct. So the only thing that is sacrosanct is that you need large betas, because if you have small betas, then what it will try to do is these constraints won't be satisfied to the accuracy you want, and it will try to minimize this beyond what it needs to. So you need to set large betas so that even if this is, let's say, satisfied up to some order 0.1, and if this is 10 to the power 6, the loss is still huge. So you really, if this is 10 to the power 6, it will ensure that this is satisfied at least up to 10 to the power minus 3, or even smaller. So with this loss function, large betas, and so then what will happen is, if these are satisfied, so this goes to 0, this goes to 0, and this goes to 0, then the minimum of the loss function is the minimum of your entanglement, first entanglement power, which was basically negative of W00. So you do this and then you can impose constraints. So I impose, for example, I impose this constraint using the neural network, and these are the leading trajectories. So again, I won't go into, all these things. So the PINN result matches the open string values pretty well. Yeah, I also impose the other constraint, but yeah, let's not get into that. Okay, thank you.
Very well.
Very nice talk. So people,
Thanks.
I have just one. I guess I'm really confused about what is the statement of this duality, because see this, the M is the function of two variables, right? S and T, and it's crossing symmetric. So I know that whatever poles in S there are, automatically there will be those poles in T, right? Because the function is just symmetric in S.
Yeah.
And what is this duality saying? Like what is extra on top of crossing symmetry?
So
Just to write in terms of one semicolons.
This 1 by S minus S square and 1 by T minus S square.
Yeah.
If you just look at the poles of T,
Yeah.
you would never see the 1 by S minus
No,
S
but
square.
the
It
one
would not be symmetric.
The 1 over S minus M square is a constant as far as T is concerned.
You don't want the constant. It doesn't come as a residue. I thought that was my
Because
understanding.
these are all congruent.
Not a residue. It's not a residue of any pole.
But yeah,
You
but
can think of a residue of T to
no,
no, but can't we have an scattering amplitude which is a bunch of poles in T? And
yeah.
just a
So
constant
let
of
me.
T, right? A constant which just doesn't depend on T.
So if there's a constant, it doesn't satisfy duality. Duality means there is only poles and nothing else. That is the statement.
That's the definition.
Yeah, only poles. Because
It's not obvious that I can write it as just the pole terms. You know what the poles are and you know the rest.
Yeah.
But poles
Because-
without any constant.
Without any-
Yeah,
that's all.
because in a sense, what you're saying is if I've taken care of the poles, then I can only have an entire function piece that is left.
Yeah.
Duality is saying these amplitudes don't need the entire piece. They only need the poles. That is the statement of duality.
Okay.